Hey, hello. This is your second assignment from Unit 9. And we're going to get a little quantitative here. Got my handy school bus colored calculator ready to go. So, number one, two objects A and B have identical velocities. Object A has 3 times the mass of object B. So I'm just going to call the velocity V. And object A has a mass of 3m, and object B just has a mass of m. So same velocity for each one. Object A has a mass of 3m, B is m. You could pick numbers for those if it feels more comfortable to you. But, I like algebra. Find the value of the ratio of momentum A to momentum B. Okay, so momentum is mass times velocity. So the momentum of object A is 3m times v. That's its mass. Oops, I used a capital M over there. Consistent. Times v. And the momentum of object B is its mass, m, times the velocity, v. So a ratio of two things, this ratio of this to this just means, that's just a fraction, that to that. You might have learned at some point in some math class or something to do like the ratio with the little dot, like the little colon between the numbers. Not a huge fan of that, am I? So I like to do it as a fraction, so that's 3mv over mv, the mv's cancel. So the ratio of A to B is just 3. You could write that as 3 to 1, like 3 to 1 if you want to, but I prefer just as a number. So what's the moral of that story? The momentum is linearly, in other words, first power dependent on mass. If you triple the mass, you triple the momentum. How about find the value of the ratio of kinetic energy of A to kinetic energy of B? Kinetic energy is equal to 1/2 mv squared. Okay, so the kinetic energy of A is 1/2 mv squared, or 3 times, it's like 1.5 mv squared, right? 1/2 of 3. And the kinetic energy of B is 1/2 mv squared, because it just has a mass of m. And then if I set up that fraction, I'm going to get that ratio is equal to 3 again. I'll let you do the math there. You get this one on top, 1.5 over 0.5. That's 3. So, not surprising, because here in the momentum equation, mass is to the first power, and the kinetic energy equation, mass is to the first power. So if you triple mass, you're just going to triple the momentum and the kinetic energy. But what if here, now we have identical masses, but object C has twice the velocity. So C has like 2v, and object D has a velocity of v. Okay, so what does that do with the momentum? So the momentum of of C, rather, is it has a mass of m, and it has a velocity of 2v. And the momentum of object D, it has a mass of m and a velocity of v. So the ratio of this over this is going to be 2. That's not surprising, because in both for the momentum of both, the velocity is to the first power. So if you double the velocity, you're going to double the momentum. And then finally, kinetic energy of C I got 1/2 mass times 2v squared. And let's see, if I square that 2, that's 4, and it's 1/2, so that gives me 2 mv squared. And the kinetic energy of D is 1/2 mv squared. If I set up the ratio, this is 4 times bigger than that. So what happened there? That's the first time I doubled the velocity, but that quadrupled the kinetic energy, and that's because the velocity here is getting raised to the second power. So an increase in velocity gets bumped up by the power of 2 here. That's the point of that whole problem, or 1 and 2, both. Number 3, following questions refer to the motion of a baseball. While being thrown, a net force of this acts on a baseball of mass this, grams, not the right units, for a period of 4.5 times 10 to the negative 2 seconds. Seconds is the right units. What's the magnitude of the change in momentum of the ball? So I know that force times change in time is equal to change in momentum. And this is just asking for what's the magnitude of the change in momentum. Well, it's just this. It's whatever the force is times the amount of time. So the force is 132 newtons times 4.5 times 10 to the negative 2. So 132 times 4.5 times 10 to the negative 2. Okay, now what are the units here for this? There's actually 2 different things you can write down here. Since I got this change in momentum by doing a force times a time, I could call the units Newton seconds, but I could also do, since it's change in momentum, and momentum is mass times velocity, that's the same as kilogram meters per second. Those are both correct. My preference, although they're both correct, is that if you got the number by multiplying a force times a time, then write it as force times time, Newton seconds. If you got whatever number you're looking at by multiplying a mass and a velocity, then write kilogram meters per second. Right? Just be true to your process there. But they're both correct. If the initial speed of the baseball is 0, what will its speed be when it leaves the pitcher's hand? Okay, well, I've already got this side of the equation. I'm just going to do this. Let me show you what I'm doing here. So times time is equal to mass times change in velocity. So unbalanced force times time, that's what we did here, 5.94. The mass of the ball is 0.140 kilograms. And then change in velocity is final velocity minus initial velocity. Initial velocity is 0. So to get the final velocity, I have to take this and divide by 1.4. And I still have that number there, so I'm just going to divide that by, did I say 1.4? Sorry, 0.14. So 42 meters per second about. When the batter hits the ball, a net force of 1,150 newtons opposite to the direction of the ball's initial motion acts on the ball for this during the hit. What's the final velocity of the ball? Okay, so same idea. Unbalanced force times change in time is equal to mass times change in velocity. So unbalanced force is 1,150, and maybe before I go any further, actually, just going to put that time in, times the... I think we need to make some decisions about direction. So this is the easiest mistake to make when you're doing impulse momentum stuff, is to just dump all the numbers in and not pay attention to direction. So let's say that the batter is here with the bat, and the pitcher is here. The ball is coming this way toward the batter, and then after, the ball is going to be going that way, right? This is the initial, and this is the final. So we need to respect directions here. I'm going to call to the right the positive direction, because that's just intuitively easier for me to do. So that means that the force on the ball is going to be in the positive direction. Like, no doubt the force of the bat on the ball is in the positive direction. Don't need to worry about the sign of the time. That's always going to be positive. And then I have the mass of the ball, 0.14, and then I have the change in velocity here. So the final velocity of the ball is what we're looking for, and minus the initial velocity of the ball is 42 meters per second that way. That's in the negative direction. So that is the mistake that is easiest to make, to not deal with that. All right, so let's see. I think I need to write out another line here. I'm going to go ahead and multiply 1,150 times 9 times 10 to the negative 3. Gives me 10.35 on this side. And then here I'm going to distribute the 0.14. This is called algebra. Got to know how to do that. And then 0.14 times positive 42 5.88. Okay, more algebra. I'm going to subtract this over to here. So 10.35 minus 5.88 is 4.47 equals 0.14 VF. And then finally, I'm going to divide both sides by 0.14. Is I'm going to call that 32 meters per second. Does that answer make sense? The ball's coming in this way with its initial velocity of 42. We call that negative because it was coming this way, and then it comes out in the positive direction with a velocity of 32 meters per second the other way. Yes, that makes sense. How large is the force the ball exerts on the bat? It's the same, because Newton's third law. Equal opposite, always. All right. Got another page here. A rocket weighing 4 points. So this, when we say weighing, this is the gravitational force. You don't have to multiply. This has already been multiplied by 10, right? It's in newtons. It has an engine that provides an upward force of this. It reaches a maximum speed of this. Right, that'd be its final velocity. Draw a force diagram for the rocket. Okay. Got a gravitational force of this much, and a lift, an upward force of this much. That's 10 to the 4th is 10 to the 5th, so this is bigger. It's It's like a thrust force, lift force, whatever you want to call it. Okay. And while I'm at it, I'm going to just write this unbalanced force is equal to winner minus loser. That's the force of lift minus that force of gravity. So the difference between those is what we're interested in. For how much time must the engine burn during the launch in order to reach this speed? Okay, so I know that unbalanced force times change in time equals mass times change in velocity. So the unbalanced force is whatever this minus this. Let's do that. 1.2 times 10 to the 5th minus 4.36 times 10 to the 4th is 76,400 times the time is for how much time? That's what I'm looking for in this problem. And then the mass, maybe this is the trickiest part here. The mass of it, this was the gravitational force. So if I want the mass, I need to divide that by 10. That's going to be 4,360. If you take that number and divide by 10, 4.36 times 10 to the 4th divided by 10 is equal to 4,360 times the change in velocity. That's its final velocity. And then, of course, it started minus 0. It started on the launch pad with a velocity of 0. So, do some math here. I need that number times 860 divided by 76,400. That's about 49 seconds. Seems about right for a rocket launch, right? To get up to that speed. All right. Golf ball that weighs 0.45 newtons, that's its gravitational force. And just while I'm looking at that, its mass, I have to divide. This is the number that's already been multiplied by 10. So its mass would be 0.045 kilograms. It's dropped from a height of 1 meter. Assume that the golf ball has a perfectly elastic collision with the floor. That's getting a little bit ahead. I didn't mention that in the notes before. That's something I'm going to talk about in your next set of notes. What that means is that it's going to bounce back with the same velocity. So however fast it hits the floor, however fast it's going right at the instant when it gets to the floor, it's going to boing back with exactly the same velocity. There's other things, or another thing that means, but I'll talk about that in the next set of notes. You don't need to know right now. So that's what that means. It means initial velocity, final velocity, same in magnitude but opposite direction. Okay, so construct a motion map for the golf ball from the time it's dropped until it reaches its highest point of rebound. So the motion map would look something like there it is, and then it's going to pick up speed there, and when it comes back, it's going to kind of like reverse the motion here. So something like that. Right, bigger arrows down here, and then smaller ones up here. Determine the time required for the ball to reach the floor. Okay, if I'm looking for time here, I think that there's a couple things that we could do. We don't know the velocity yet, so I don't think we can use this, because if we're looking for the time, we'd have to know all the other things, and I don't know that change in velocity yet. So I'm just going to do the kinematics approach to this, where I'm dropping something, so I know the acceleration is negative 10 meters per second squared. I'm dropping it, so the initial velocity is 0. I know that it's going to fall, negative sign, it's going to fall 1 meter, and I'm interested in knowing what the time is. What's the equation that relates those things? That is the delta y equals 1/2 at squared plus VIT. The VIT is gone because that's 0. So I have delta y is equal to 1/2 a times t squared. So t is the square root of 1/5. And 0.45 seconds. Okay, got that. What will the instantaneous momentum of the golf ball be immediately before it strikes the floor? So that's just momentum is mass times velocity. Why does it say instantaneous momentum instead of momentum? It could have just said momentum. Instantaneous just means like right at that instant, like not when it hits the floor, not when it's changing direction, just right as it gets to the floor. So momentum is equal to mass 0.045 times the velocity. Oh, I haven't figured out the velocity yet. Okay, so here we have a choice. I could go and do kinematics and figure out that velocity, or I could say, hey, I know that force times time is equal to change in momentum. So I could do that. The force on the ball is just the weight of it. It's mass times 10 times 0.45 seconds. And that's equal to the change in momentum. And since it started with 0 momentum, that is its final momentum when it gets to the floor. So that's an approach. You could do kinematics and then do the mass times velocity. Maybe I'll do it both ways so you can see that it comes out to be the same thing. So I'm just multiplying 0.45 by itself. That's about 0.20. I'm going to call that, since I got that by multiplying a mass times, a force times a time, I'm going to call that Newton seconds. Okay, and then over here, same problem here, but what if I wanted to know its final velocity? Then I would use the equation Vf squared is equal to Vi squared, that's going to be 0, plus 2a delta y. So Vf squared is equal to 2 times negative 10 times negative 1. So Vf squared is the square root of 20. Which is about 4.5 meters per second. So then 4.5 here, and that gets me 0.045 times 4.5. Hey, 0.20. I got the exact same thing. And this one, I'm going to write the different units, kilogram meters per second. They're the same. I wrote it this way because this one I got from multiplying a mass and a velocity, and here I wrote Newton seconds because I got it from multiplying a force times a time. Those are the two ways to get that. What will be the change in momentum, delta P, from the instant before the ball collides with the floor until the instant after it rebounds? Okay, so if its velocity is this, what was it, 4.5 meters per second in the down direction, perfectly elastic collision means same velocity but exactly opposite direction. It bounces off the floor. So it's going to be 4.5 that way. So same problem, same issue with these momentum problems. You've got to make a decision about direction. So here, I'm going to say that this is negative and that this is positive here, negative and positive. So if I want my change in momentum, that's equal to mass times change in velocity, final minus initial, 0.045. Final velocity is 4.5 up, positive, and the initial velocity was negative. So, calculator, so it's twice as big as this, right? Because it changed from having that much momentum down to that much momentum up. So the change was twice as big. I feel like I got that from doing a mass times a velocity, so I'm going to choose those units. E, suppose that the golf ball was in contact with the floor for this much time. What was the average force? So if I know what the change in momentum is, then I know force times change in time is equal to change in momentum. So is equal to, the change in momentum is 0.40, and I'm going to divide by time here, 4 times 10 to the negative 4. That gives me, let's see, 0.4 divided by 4 times 10 to the negative 4 is 1,000 newtons.